Harry also. Yeah, I think we can start. Okay, so are you ready to start?
Sure.
Okay, very good. Then welcome everyone. Today we're very happy to have Jérôme Pernot from the University of Caen, Normandy. And he's going to be talking about Berkovich compactifications of complex analytic varieties. So please.
Thank you. So first of all, thanks a lot for giving me the opportunity to speak here. That's a really nice invitation. And so, yeah, I would like to speak a bit about my work on Berkovich compactification on complex analytic varieties. So it's probably going to be more of a kind of overview of the general theory. Yeah, maybe let me show how it goes. Like in simply very just two parts. Like probably a first part rather introductory to like the theory of Berkovich spaces. So maybe you've seen a bit of that over field, but you can also have a theory over Banach rings, a bit more general objects. And so I will recall like the basics of this, try to make you feel how it looks. And then I talk a bit about the compactification. So the basic motivation here, I'll come back to it later, but it's to find some, say, natural, canonical, okay, something like that, a compactification of complex varieties. And my point is that it's possible to do it within the framework of Berkovich spaces. Okay, so yeah, and please don't hesitate to ask questions during the talk. I'll try to keep an eye on what's going on in the class. Okay, so let's start with Berkovich spaces. So let me first begin with Berkovich line, so dimension 1, over some valued field. So we start with K, so just some complete non-Archimedean valued field. And so the definition of the Berkovich line, say, as a set is that's Berkovich definition, so the set of multiplicative semi-norm that extend the given absolute value on K. So multiplicative semi-norm is, yeah, maybe I can write something. You could think of it as some absolute value, but some absolute value with kernel. So like the important condition is the multiplication, the multiplicativity. So it just, if I write down like a few axioms, it's something like, so multiplicative semi-norm. So it goes from the polynomial to non-negative real numbers. And so some, maybe some kind of absolute value, semi-norm. And so you want that, okay, you want the triangle inequality and the multiplicativity condition. Okay, and you probably want something, yeah, something reasonable, like the absolute value of 0 is, okay, I said that it extends the given absolute value, so this is automatic. Let me just keep only those two. So that's just very some simple axioms here. And okay, yeah, this is going to disappear, but never mind. Okay, and the topology, so that's just a set. So I'm gonna give you a more precise example just right after that. And you define the topology in a quite simple way. Just you take some polynomial, and you consider all the points, so the multiplicative semi-norm. When I denote it, I mean, like this, you see here with the subscript x, it's some point that I consider as a multiplicative semi-norm. So points of the Berkovich space correspond to multiplicative semi-norm. So the points where the absolute value of p is between any two constants. So that's going to be an open set and a basis of open. And this has nice topological properties. So the space is Hausdorff, it's path connected, locally path connected, and locally compact. That's some very general statement about Berkovich theory. Okay, so just for a definition. So maybe yeah, this says, so, okay, what does the picture look like in the trivially valued case? So we consider some field K endowed with the trivial valuation, so the trivial absolute value, which I'm going to denote like this. So the trivial absolute value it says that, okay, maybe I can write it down, but it's something very, very silly. You just send, sorry, problem with my pen. Okay. You just send any x different from 0 to 1 and 0 to 0 because you have to. Okay, and then you want to look at somehow all the absolute values on, so recall, yeah, those points looking at the Berkovich point are just the multiplicative seminorm on the ring of polynomials. So like this. Okay, so basically you're looking at absolute values on the polynomials. So we know, I guess, a lot of them, and maybe we are more used to looking at valuation. So we have one specific valuation, which is like maybe the t-adic valuation. So that I can denote by v subscript t, and so you take any polynomial and you associate the index of the lowest coefficient, like I don't know, if you the t-adic valuation, if you take a polynomial such that, like, I don't know, t squared plus a t to the 5, that's just 2. Okay, and you have the usual nice property that the valuation of a sum is at least, maybe I can write that, the valuation of like a sum is at least the minimum of the two valuations. And the valuation of the product is the sum of the valuations. That's pretty easy to check. Okay, and so this is not, of course, an absolute value. You see that basically the first inequality, like it does not look at the triangle inequality. It's reversed. So we just play some little trick, and what it's going to be an absolute value. It just you start with some real number r between 0 and 1, and you take this r to the power of the valuation, and this is an absolute value on your set of polynomial. So you see you have some normalization factor, this small r that appears here, and gives you like some continuous family of absolute value. So this is something that I can draw on my picture of a Berkovich space. So it looks like this. Maybe I put some segments, say, here. Yeah, sorry, just, yeah, technical problem with the pen. Let me try to, okay. Yeah, better. So this is some segment. So here R goes from 0 to 1. Okay, and so this belongs to the Berkovich space. This sits, like this real interval sits inside the Berkovich space, and it's actually something quite quite usual and quite interesting to have those real segments inside the Berkovich spaces. Okay, so now what happens at the boundary of this segment? So if you go to r equals 1, it's pretty clear what it goes. I mean, you just take 1 to the power the valuation, and of it, you get the trivial absolute value here on the ring of polynomials. Okay, and if you let r go to 0, what happens? Basically, all the elements have absolute value 0, except those who have a valuation 0. so if you look carefully at this, so you can describe it as a limit, and it's going to give you an absolute value. I mean, not an absolute value, actually a semi-norm. Another way to do it is is like this. So the associated semi-norm is something like, so you start with some polynomial, and you evaluate at the point 0. Okay, 0 and the t-adic valuation are of course related, just 0 is the root of t, and you compose with the given absolute value. So this actually is some general procedure. You start with any point in the field. You can always evaluate your polynomial at this point and compose with the given absolute value, and it gives you a point of the Berkovich space. So that's the way it looks. And of course, here I just chose the t-adic valuation, but I could have chosen many other valuation. Like for any point, maybe a, I can do the same thing with some t minus a adic valuation. Or and I can do many branches like this that all look the same and that all branch onto this trivial absolute value here. Okay, and you can also do the same with basically any irreducible polynomial in your field. And that's almost a complete picture of what happens. You just need to add one more branch that, maybe let me do it in this direction, which basically correspond to the valuation with respect to t to the -1, t inverse. And instead of writing this t inverse, I would write in equivalent way that r, some real number, raised to the degree. Like the degree, as if you look at this property here about the evaluation, if you if you look at the degree, you see it behaves with the equality reversed, and so more as some absolute value. And this time r needs to go from let me see, pen, r goes here from 1 to plus infinity. Yeah. So this is okay. This is just this is my complete picture actually of what the affine line on the affine Berkovich line. So I denote it like this, Berkovich notation, on the trivially valued field. So just like a start with a central point and a few branches going out of it. Okay, so that's the first example to keep in mind, maybe. Okay, that clear so far? Yeah. And okay, so that's already an interesting example for what we're gonna do next. And so now let me pass to more maybe intricate picture. What happens in the non-trivially valued case? So we'll not spend too much time on that, but still explain a bit. So if k is non-trivially valued, so we still have, so let's say this time k is going to be arbitrary. So there are still some points we can describe. The first is exactly as I said before with the point 0. So you pick any point, say A, in the field, and you can associate a Berkovich point to it by this same recipe. You start with a polynomial, you evaluate in A, and you compose with the given absolute value. So this is a multiplicative semi-norm. Yeah, maybe I forgot to tell you this before, but this is also a point on not considering only absolute values, but multiplicative semi-norm. Of course, this one has a kernel, the ideal generated by t minus a, and you want to have them, of course. You want like usual points to be a point of your Berkovich space. And so for this reason, you need to allow some kernel to your absolute value, so to speak. So this gives some embedding of the field k into the Berkovich line. And you can do, in the non-Archimedean case, you can also do things that are a bit more original, say. you do it like this. So you start with, let me write it here. So I still get some space for the picture. So you look at a polynomial and you just write it with the basis that the powers of t minus a, with some coefficient like this, ci t minus a to the I, and you send that to the maximum of the absolute value of the coefficients times r to the I. And you can check that this is multiplicative. Here you use in a crucial way the non-Archimedean triangle inequality, or otherwise it's completely false. Over C, for instance, it's certainly not multiplicative. And this is actually quite close. Yeah, maybe I put some equal sign, which is a bit okay. There are some condition, but rather mild condition, I say. So this is very related to the supremum norm on the disk of center A, radius r. So these are two kinds of points that you find in your space. Okay, and okay, and now if we want to draw a picture, so from some arbitrary k, let me, I don't know, put some point A here, and so I draw some line like this with those points. Like that. So on such point, I denote by eta AR. So that's the associated point. Okay. And of course, you can let R vary from 0 to plus infinity. So you still have this half line, real line inside your Berkovich space. And now you have many, you can start with another point, say B, and try drawing segment like that. Okay, so maybe you want me to draw something like this with the eta bs, but actually it's not exactly this that's going to happen because of the non-Archimedean situation. So I just said that the point corresponds to sup norm on some disk, so disk of radius of center A first, and then disk of center B. But in the non-Archimedean world, you cannot really point the center of a disk. So you can choose the center of the disk as being any point in it. So at some point, when your radii get big and big enough, A and B are going to belong to the same disk, so they're going to give rise to the same absolute value. So actually, my two segments that I want to draw look like something like this. So they are going to meet at some point. Yeah. Here. And so this is, so you have some, say, eta bs here for S growing. And the thing is that you have that when you reach the distance between A and B, the 2 points coincide because the disks coincide, as probably well known. So it just, okay, and you keep on writing things like this, so adding branches out of many points. And depending how close your points are, so if I have a branch here, the corresponding point C will be closer to A, like the distance between A and B will be small compared to the distance between C and B, and so on and so forth. And you continue drawing like that, and you end up with some kind of tree like this. So it's probably quite a familiar picture if you've ever heard about Berkovich spaces before. So in dimension 1, it's something like this. So that's for the arbitrary valued field. In the trivially valued case, as we did before, you just get some degenerate picture when okay, you have very, very little branching only at one special point associated to the trivial absolute value. Okay, so yeah, that was yeah, maybe something I did not say or I didn't mean to say anyway. So this is not a complete description of the Berkovich line over an arbitrary field. So you have some points to add. So I don't want to go into this. It's not going to be useful for the talk, but yeah. So keep that in mind. But I mean, the picture stays basically the same, and all the properties are fine here. Maybe Okay. So try to keep this picture in mind. So that's what we want to for the one-dimensional Berkovich spaces. It's something that looks like this. Okay, so let me go a bit further. Yeah. No.
So can I ask maybe a question about this?
Sure. Yeah.
So you mentioned the embedding of K into the affine line, and so
Yes.
it can happen. So the affine line, I guess, is uncountable even if K is countable or something like this, or
Indeed, yeah. You have, as I said, you have real segments inside the
yeah,
Berkovich line.
yeah.
So
But
yeah.
is this image of the embedding still dense or something like this, or?
Well, it depends. It depends a bit. So you see in this first picture that was there. So the embedding is no, that's not okay. I didn't. Yeah, maybe I should say a word about the topology. I won't do all the computation maybe, but see if I get back to the definition, you see you want to understand how the polynomials behave on your tree, basically, on your space. And so, yeah, I mean, in the trivially valued case, for instance, you can have, like, the first thing we should check, I mean, basically didn't say it, but I guess it was clear that the segments I draw on my picture are really homeomorphic to usual real segments. For instance, I don't know, maybe I do it in blue. You can have so this here, so that just some small interval. This is an open set, and you can define it by say absolute value of t. It's gonna be I don't know. Maybe I put some numbers like 1/3 and 1/2. Okay, and this is an open set by the very definition of the topology. And you see that here you don't have any points inside this open set. Okay, like the only points coming from K are at the end of the branches. Okay, so here the K points are not going to be dense. Okay, and now if I go back to the other picture, probably if I want to draw the same picture here. If I say absolute value of t between two values, if k is not trivially valued, I mean, there could be that there are many points with absolute value of t between those those two bounds I chose. And okay, actually, so it's more yeah, so K points are not actually done. So there another thing you should be careful with is that any point in the algebraic closure of K also gives rise to a point in the affine line over K that's at the end of the branches. So in the so maybe I can just write this. So you have an embedding of K bar and even its completion into the affine line over K. Oh. Okay, and okay, so some points are going to be identified. You should mod out if you want an injection by the Gara group, and this is dense if your field is not trivially valued. Okay.
Oh, I see.
And okay, I didn't say a word about the topology, so maybe I don't want to say too much, or yeah. But like if I want to draw some open sets, like some typical open set would look like this. Yeah, maybe if I want some open set, let's say a typical open set would be, try to find some space to write something, maybe here, like you take some some polynomials, say t minus a, and you okay, you multiply by some t minus b, and you put two constants. I don't know, just some random sim alpha, beta. So what does it look like? So you see that you should cut off some part of the branch out of A, maybe some part of the branch out of B. I don't know, somewhere here. And if you do things maybe here, like the degree would be somehow bounded, and then you get all the remaining branches entirely. So that's a picture is something like this. So in some sense, like the open sets are very big. So of course, this one contains a lot of ends of the trees, and so the k-bar points are going to be dense. Okay, so this is really a typical open set. Open sets are big. You should see that. I mean, something I didn't say that, I mean, it looks like a tree. So the real segments are homeomorphic to usual real segments, but it's not what we usually call the tree topology. It's like a coarser topology, and it's necessary if you want to have some compact space. Okay. Like the tree topology would be you are allowed to cut every branch out of a node wherever you want, so that's not possible. Here, if you take a branching point and a neighborhood of this point, you need to take entirely all the branches out of it except a finite number of them. So that's very big open sets, and that's something necessary if you want the resulting space to be compact or at least locally compact. Okay.
Mhm.
Yeah. So yeah, it's good to have an idea of these topologies. Yeah. Thank you for the question.
Yeah, that was very helpful. Thank you very much. Yeah.
Sure. Okay, great. Yeah, so let me go on. Okay, yeah, I wanted to okay, you can see the title if I do this. Maybe how can I remove that? Ah, là. Yeah. So complete residue field and structure sheaf. So Berkovich spaces are actually not only topological spaces, or even less like just sets. You have more than that. I mean, what we use them for usually is just as some analog of the complex analytic spaces in a non-Archimedean world. So you really want to define on them some notion, well-behaved notion of analytic function. So basically, in like a more fancy language, you need some structure sheaf with some kind of analytic functions on it. So you do this in two steps. So first, you take a point, say x, so associated to some multiplicative semi-norm, denoted like this here, and so you want to compute to build some residue field. So basically, as in the scheme case, so you just take k of t. You mod out by the kernel of the semi-norm. It's a multiplicative semi-norm, so the kernel is a prime ideal. So here you have a domain, so you can take the fraction field, and on the fraction field, the semi-norm induces an absolute value because you killed the kernel, so you can pass to the completion. And passing to the completion is what we call the complete residue field, so the residue field, if you want, in the sense of Berkovich theory. So you start with a complete valued field K, and you want to get back a complete valued field as a residue field. So this is this curly h of x, and the general things told you that you have some evaluation map. Okay, so to each point, you associate some residue field that, of course, depends on the point. Okay, and then, okay, this is a definition of the structure sheaf. So you take any open set, and you take maps that go from U to the disjoint union of the residue field. So it's a bit silly, just saying that to each point x in U, you associate some value inside inside the residue field. Okay, so it's written here downstairs. And you add one more condition to recall that you're doing analytic geometry. You want f to be locally some uniform limit of rational function without pole. So I said before, you have a map from the polynomials to h of x. You have a map from the rational function to h of x, and it makes sense to speak about uniform limit of rational function. So this is more or less what an analytic function should look like. And this is what happens in Berkovich theory. So just to tell you that there exists a very general definition in this setting. So yeah, let me not spend too much time on that. Okay, and maybe, oh yeah, you have usual properties like coherence of the structure sheaf, as we are used to in the complex analytic setting, analytic continuation, I mean, for like normal spaces, etc., and so on and so forth. Yeah, maybe I think I already spent enough time on pictures, so maybe I just skip this one. So just to show you what the structure sheaf looks like, but it does basically what you want it to do. Like if you can define some open disk, and then the open disk, the section of the structure sheaf on an open disk would just be power series with the radius of convergence prescribed by the radius of the disk. So exactly the same thing as we are used to in the complex setting. Okay, let me just skip this. And so now I'd like to go to a more general theory. So, okay, so yeah, maybe just let me sum up quickly. So I just say the example of the affine line, but okay, like general Berkovich space would look the same, except there are higher dimension. So define in terms of absolute value, and you get some locally ringed space with nice property, this Hausdorff local compactness, blah, 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 everything very close to what we have in the complex setting. So that's somehow the usual Berkovich theory. And okay, if you look at Berkovich's book, in the first pages of the, I mean, it like, I don't know, like 90% of it is devoted to spaces over a field. But if you look at the first few pages, he has a very general definition of Berkovich spaces. I mean, analytic spaces, he calls them, of course, over some Banach ring. So let me tell you what it is. So you start with a Banach ring. So I didn't put the definition, but it's something like non-surprising. So A is of course a ring. So the norm, maybe the only thing that the norm is submultiplicative. So the norm of A of the product is at most the product of the norms, like this. And Banach means that, I mean, of course, you want to send 0 to 0, 1 to 1, minus 1 to 1, thing like this. And Banach ring means, of course, that the ring is complete with respect to this norm. Okay, so far so good. Then, yeah, examples. So any complete valued field is a Banach ring, but you have more fancy examples like Z, the integers, and those with the usual absolute value. Of course, you have a discrete topology on it, so it's certainly a Banach ring. Or I come back to this example later, maybe. You can take the field C, but not take the usual absolute value. You could take this norm, which is the maximum, the trivial absolute value, and the usual absolute value. So this is the example I want to use in this work about compactification. So I'll come back to it later. But for the moment, I just want to show you the definition of the Berkovich space over a Banach ring, and it looks exactly the same as before. So here I wrote like two definitions, the spectrum M of A, so that the Berkovich spectrum, or another way to say it is that the space of dimension 0, and I also put the definition in of the affine line over A, and both are sets of multiplicative seminorm. So multiplicative seminorm on A for the spectrum, on A adjoint T for the affine line, and you want that your point, the associated seminorm, is bounded by the given norm on the ring. Okay, so it's still very close to what we have in the case of fields, of course, and yeah. And actually, we define everything the same way. That's quite nice with Berkovich theory. You have really a uniform definition. So you can define the topology as before. You take elements of A or elements in A bracket T, and you say that you define open set by demanding that the norm of those elements are between two bounds given a priori. You can define complete residue field, you can define the structure sheaf, and the usual properties I mentioned before still hold, at least in the three examples I wrote upstairs. valued field Z or C with this so-called hybrid norm. Okay. And some interesting things is also looking at fibers. So you have a map like this from the affine line over A to the spectrum of A. So it should be pretty clear. So you take a point in the affine line over A. So but by what I just wrote above, it's a semi-norm on A bracket T. So it induces, I mean, you can restrict that to A, and then you get a semi-norm on A. So that's the point of the spectrum. So that's just the projection, geometrically speaking, is just the restriction from A bracket T to A. Okay. And now if I take a point downstairs, some point X in the spectrum of A, you can look at the fibers over this point, and it's maybe what you would expect from that the usual algebraic geometry, scheme theory, etc. The fiber you identify with the affine line over the completed residue field, which is the thing we defined before. So this tells you that if you want to describe the affine line over A for some Banach ring A, what you need to do is to describe M of A, so the somehow like the base space, and then the fibers, which are all affine lines over some valued fields, so basically of the sort we described before. So if your field is trivially valued, it's just like this star with one central point. Otherwise, if h of x is not trivially valued, you have a tree with a lot of branching everywhere. And all of this gets put together inside in those spaces. Okay, so maybe something. So there's some subtle point here. I said that Banach ring include, I mean, as example, I said that you have complete valued fields, but I didn't say that those are non-Archimedean. In the first part of the talk, I said I really only considered non-Archimedean fields, but then, I mean, a Banach ring, like the C, the complex numbers endowed with the usual absolute value, is certainly a Banach ring. So the definition of Berkovich space makes sense in this setting. So let us have a look at what it gives. So now I look at the Berkovich line over C with the usual standard absolute value. Okay. So as we can do as we did before. So you pick any point Z in C, and you can define the semi-norm by taking a polynomial, evaluating at D, and composing with the absolute value. So this is a semi-norm. So it gives you, as before, an embedding of C into the affine Berkovich line over C. And actually, this is a bijection. The proof is basically Gelfand-Mather theorem. So if you want to go the other way, you pick a point in the Berkovich space over C, and you look at its residue field. That's probably the easier way to do it. The residue field is, by definition, some complete valued field that is an extension of C. And Gelfand-Mather theorem tells you that such an extension of C with a valued field containing C has to be C itself. So the extension is trivial. So the only residue field that you get are C, and from that it's easy to show that you actually get a C point. So this is a bijection. Actually, this is much more than a bijection. This is a homeomorphism first. I mean, so I told you that the topology on the Berkovich side was defined by open set given by polynomials and things like that. So these are certainly continuous on the usual side, and on C, like you can define the topology, for instance, using disk, and disk would be example of the open set I gave. So it's really exactly the same topology, and it's even an isomorphism of locally ringed spaces. So you need to show that you have the same definition of analytic functions. So if you take a usual analytic function of C, of course, you know that you have a Taylor development of, so it's a limit of polynomials, okay? And on the Berkovich side, I say that my functions were a limit of rational function without poles. And if you are on C, a rational function is an analytic function, and we know that analytic function are stable under uniform limits. So you really get the same definition. So this is like another maybe fancy way to recover C with the usual analytic structure, just like Berkovich definition gives you this. And okay, maybe it's worth noticing, because I'm going to need it a bit later, that this works similarly for powers, non-trivial powers of the usual absolute value. You get the same space with some kind of different normalization of the distances if you want. Okay. So that was just for C. So why am I explaining this? Just because of this picture here downstairs that tell you that if you want to describe the affine line over A, you need to describe M of A and the fibers. And I claim that some of those fibers can be analytic lines over C, so just usual complex spaces. Okay? Now, yeah, this I'll just go quickly with this picture maybe. You take Z, the integers with the usual absolute value, and you have a picture like this. So this is a space I love and studied a lot. And we know actually what this space looks like the base space, M of Z. You just want to describe all the semi-norms, multiplicative semi-norms on Z, so basically all absolute values on Z. And this is given to you by Ostrovsky's theorem. So you know that you have the usual absolute value that I just put upstairs here. You have powers of the usual absolute value that can degenerate to the trivial absolute value, and then you have all the possible p-adic absolute values. So you have infinitely many branches, one for each prime number, and this gives you a family absolute value. So this, the spectrum, Berkovich spectrum of Z looks like this. And if you want to look at the affine line, then you should put like this picture downstairs and look at fibers over those points. And so you have fibers like that can be p-adic analytic spaces when you are over a p-adic absolute value, or that can be complex analytic spaces like C when you are over a standard absolute value. So, and all those spaces are put together into a nice space. I mean, a space with nice properties anyway. Okay. And last, I mean, what's going to really be the subject of the talk is the space over C with the hybrid norm. So this hybrid norm is exactly this. So the maximum between the trivial absolute value and the usual absolute value. So something a bit strange. And we can describe the spectrum of this ring. It just, so all the powers, non-trivial, the powers of the usual absolute value and the trivial absolute value that is somehow a degeneration of the absolute value, usual absolute value raised to the epsilon when epsilon goes to 0. Okay, and I think I wanted to draw a picture here. So what does it look like? Let me take my pen. Okay, so first I can draw so the hybrid C, something like this. Do it again. Yeah. Very good. So you have here the usual absolute value. Here the trivial absolute value. And in between, powers of the usual absolute value. Okay. And okay, let me have a look at this map. So the affine line over this absolute value. So I told you that over the usual absolute value, the residue field here is going to be, yeah, maybe I put the residue field, so the h of x, this residue field here just C, but endowed with the usual absolute value. Okay, I mean, the residue fields are actually going to be C everywhere, but the residue field is a complete residue field, and it's not only a field, it's a valued field. So it fields that come with some absolute value. Okay, and so here, over the point there, I should draw the Berkovich space over C with the usual absolute value. So it's exactly so that the usual the usual complex numbers. So that's just a copy of C, and you just get copy of C everywhere over all the point with the where absolute value that are powers of the usual absolute value. But when you reach the final point, the one associated to the trivial variation, of course something different happens. You got the same picture as I drew in the first slide, which something look like this degenerate picture of a tree. So that just the affine line over C endowed with a trivial valuation. Maybe I put a 0 here to record this trivial valuation. So you just have some family like this that somehow looks as something is degenerating. So you have just a family of planes, like the usual complex planes, but at some point it becomes a tree. Okay. But that's, I mean, we didn't do anything specific here. We just look at the definition, apply it, and this picture somehow pops up. Okay. And yeah, so far that was for the affine lines. So maybe just one word about more general spaces. So I gave the definition for the affine line using A with one variable added everywhere. So of course you can add n variables for any n if you wish, and you are then going to define the space of dimension n, the affine analytic space of dimension n, and then for arbitrary analytic spaces, you just consider open sets of affine space, analytic subsets of them, and glue everything the way you like. Okay, so just a very general theory, just as you define complex analytic spaces by first looking at C to the n, then open subsets, then closed analytic subset, and do some gluing. Okay. And in the cases I mentioned before, valued field, Z, C with the hybrid norm, the analytic spaces have all the nice property you expect, local compactness, local path connectedness, coherence of the structure sheaf, and so on and so forth. Okay. And something also that's very useful for us. So there is some analytification functor from varieties over A, schemes of finite type if you want, to analytic spaces over A, and this preserves many properties. So I guess it's clear. I mean, it should be clear how to construct this functor. Like the analytification of the affine line is just the affine analytic line that I defined before. Same for AN, and then you can pass to closed subset by taking just the same equations. So the analytification functor is pretty clear to define, just the same as you do for complex spaces. But you have a general theory allowing this. Okay. So that's my quite general, bit lengthy introduction to this general spaces of the general Berkovich spaces. Okay, so I hope it's more or less clear so far. And what you should keep in mind if you got a bit lost, so it's something like this picture. So you have this family of spaces, complex spaces that degenerate onto a non-Archimedean space. And the thing you should also remember is that it's not just a collection of fiber. That's really a space. It's defined as a whole space. Okay, of course I can look at the projection, but it's really a space in its own right, with nice properties as a topological space, like locally compact, locally path connected, whatever. And it's an analytic space. So you have very much more structure than just a collection of fibers. You can define global functions on such spaces. Okay. Questions? Okay, if not, try to go to my second part, which is about compactifications. Okay. So yeah, if you got a bit lost before, yeah, I'm sorry about that, but you should you get an opportunity to get back on track with me here. So I'm just kind of starting from something new. Okay, so what do we want to do? What the problem is? So we start with some, say, algebraic variety over C. Say that, okay, everything I'm going to say, just let me say just once. I'm going to say C everywhere from now on. If you replace C by any valued field, complete valued field, Archimedean or non-Archimedean, it works exactly the same. If you like, you can say QP instead of C just everywhere, and it works exactly the same. But maybe for concreteness, let me stick to C. Okay, so start again. Given an algebraic variety over C, we would like to define some compactification of X of C. So when I say X of C, this is really the complex analytification of X. So with the transcendental topology and the analytic functions in the structure sheaf. So I would like to define a compactification, which I denote like this, with X with a corner, such that we have some nice property. So first, maybe it's canonical. That just I give you, if you give me X, I give you a compactification, no additional choices involved. And I would like that X, the compactification preserves the properties of X, the topological property, the algebraic properties. And maybe also in many cases, it's usual to have to preserve like modular interpretations. Like if X is, I don't know, a moduli space of something, a moduli space of curves, of abelian varieties, of whatever, you would like the compactification to be still a moduli space of some objects related to the former. Okay. Of course, this is not so easy, and it's pretty hopeless if you want to stick to the category of variety. Like you start even with A2. Okay, it works fine in dimension 1. Okay, but then if you in dimension 2, you start with A2, and you have many possibilities to embed it as a variety into bigger compact or proper varieties like P2, P1 times P1, and you can blow up those as much as you want. And you have really a lot of embedding, and it's not clear which one should be better than the other. And actually, it could also depend on the problem you want to tackle. Okay, so nothing much to expect here. So we try something else. I mean, we try, people try that before. And the idea is to use valuation. So, okay, maybe ideally we would like to stay within the realm of variety, but this will not work. So we try some new idea, go to some bigger spaces, and we can use valuation. So it's already something that's been implemented, I guess, by Zariski with the Zariski so-called Zariski-Riemann spaces, also by Morgan-Shallen more concretely when they studied some representation theory. Okay, so well, I would like to show you now that it's possible to really do this within the framework of Berkovich spaces over the hybrid complex numbers, and that you can get more or less all the properties you want in quite natural way. So we want to compactify something. So let me first define the boundary. So I give a definition here, maybe with not so much definition. The thing is that this definition appeared before, especially in the work of, so there's a letter from Berkovich to Drinfeld. That's also some work of Thuillier. So some people was there, and okay, maybe they didn't exactly phrase it like this, but it's clear when you think about the problem this way that this should be the boundary. So here is the definition. So we start with variety over C. I look at its analytification over C with the trivial valuation. So I'm going to denote it like this with the 0 downstairs to recall that it's a trivial valuation. So this is a non-Archimedean space. So if X is A1, it's just like this star with just one central point before, like maybe some kind of a spider. Okay. And I want to define the boundary like this. So I don't take all the analytification, but I remove many points with, as multiplicative seminorm that have some center on the variety X. I think I put the definition of the center somewhere here. Yeah. Okay, maybe if you see it for the first time, it's not so clear what it means. But having a center, meaning that so you have a map, you take a point in the analytification. You can always send it back to the scheme. So your point has a kernel. It's a seminorm, it has a kernel. The kernel is a prime ideal, so it's a point in the scheme. And the question is like, can you extend this map to the spectrum of the associated valuation rank? Okay, let me not spend too much time on it. But I mean, if you're familiar with this, it should be quite reasonable. So we want like, okay, I mean, first, usually valuation of center, not multiplicative seminorm, but it's just an extension of the usual definition. And okay, you want to look at all the seminorm on your space, and if you have a center on X, what we want to say that we already have this point, we don't need to add something else. Okay. And so we just, and the other thing is that you know that if you have a proper variety, then every evaluation is going to have a center. Okay, so it's more or less the idea. So we look at some compactification of X, then every valuation has a center in it, and but we want only to keep the valuation that have not already a center in the variety we started with. Okay, so this is the abstract definition. So you take all valuation, remove those that already have a center. So let me do it in more concrete terms, maybe. It works like this. So yeah, all the valuation minus those who have center. So the so-called internal definition would be this. If X is spec of A, so some affine scheme, I can give you the definition or characterization of this X bet, the point with the center, as M of A, meaning you take all the points where all the elements of A have absolute value less than 1. Okay, so just very clear definition. And you also see from that this X bet, that's a Hebrew letter, is compact. And so the X infinity, so which is going to be the boundary, is open. Okay. Now some external definition, which is also quite interesting. So first you need to embed X in a proper variety Y and look at the boundary Z. And so maybe some divisor at infinity, something like that. And if Z is defined, at least locally, by the vanishing of some function f1, fr, then you have a concrete description of the boundary by requiring that the maximum of those functions is strictly between 0 and 1. So this is this is like a puncture neighborhood of your variety. And the nice thing is that it's independent of Y. Maybe if I want to draw some picture. So like, I don't know, you would have, maybe this is like, this would be Y, and I have some, I don't know how to draw a boundary. It's not so clear, but yeah, especially if my pen doesn't want to work. So let's say this is Z. And now this X infinity is something like, so Z is defined by the vanishing of all F. So it's like max of the Fi is 0. And then you take something a bit bigger. So the max of the Fi is something that max of the Fi is smaller than 1. So some neighborhood of the Z, the part at infinity, but you remove the Z because you want the max to be more than 0. So like you remove something like that. So it's exactly some kind of puncture neighborhood. So you take a neighborhood and then you remove the thing you started with. So it really looks like a neighborhood of infinity. Okay, and the nice thing is that, so I define this with some compactification Y, and of course it does not depend on the compactification because we have the other definition that is just independent of it. So it also says that if you do this definition, like take some puncture neighborhood of the divisor at infinity, and if you do it in different compactification, you actually end up with the same space if you do things properly. Okay, and let me just stop for 1 minute telling you about Thuyet's result, who studied and actually introduced this bet notation and kind of thing. And he has a very nice result about this boundary that I cannot resist to tell you about. So you embed X in a proper variety with normal crossing boundary. So something a bit more specific than what I said before, but we can do that. And you consider the dual complex of this divisor Z at the boundary. So dual complex means meaning that you probably have, Z could have several irreducible components. So you can define some complex by you just put some point, 1 point per irreducible component. And then if two irreducible components intersect, then you put some edge between the 2 points. Okay, and you go on like this. If you have like a triple intersection, you are going to fill in some triangle between some edges and so on. So it gives you a very nice complex, so nice topological checks. And Thuilier's result tells you that this dual complex has the same homotopy type as this boundary x infinity that we defined before. And in particular, the homotopy type of this dual complex does not depend on the compactification you started with, which it's certainly not obvious a priori. Okay, so you have another proof of that by Stepanov that a bit more intricate. That means you need to relate two compactification, and if you know how to pass from one to the other by a sequence of blow up, blah blah blah. Okay, like some fine enough version of resolution of singularities, you can try to control how your dual complex moves, and you could get the result. But this is like a non-Archimedean proof of this, which is also quite elegant. Okay, and this kind of argument tell you that this x infinity, is really something intrinsic and should really look like some boundary of the space. Okay, let me go on. I want to draw, to draw some examples. What does the boundary look like? So I will do two examples, the affine line and the affine plane, I guess. So the affine line, spec of C bracket T. So I said that the x bet is this. So just you have this absolute value of T and you want it to be smaller than 1, that the part with where the valuation have the center on the affine line, that the part you want to remove. Okay. And okay, maybe I want to draw a picture here. If you picture, yep. If you remember, so I drew this affine line before, of course. So it was something like this. Yeah, sorry, I think I left some space here. Is this right or not? Yes. So I can draw here. So this affine space over C with the trivial absolute value is just something like this. So we had like the t-adic valuation, all the possible valuations. Okay, we had the VT minus A, blah, 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 blah. And one part going up with the degree. So this was, so R2. Yeah, maybe this point's a bit too big. Yeah, like this point is going to be R to the degree. I should have wrote on the pen, but okay. And so now what happens? You see, so this is just the analytification, the thing I drew before. And if I want to look at x infinity, I want to remove, or maybe x, so x bet. X bet is where the absolute value of t is smaller than 1. So it's smaller than 1 basically almost everywhere. So in the trivial valuation, when you apply the t-adic valuation, when you apply any valuations to respect to any polynomial, so the part you remove is this one. And so the part you keep is exactly this one here. This one here, so it's an open part. I'm not sure if it's clear. So the point here is red. Okay, so you just have some oh, sorry, one color. You just have some small interval upstairs that you keep for the boundary. Okay. So maybe it's a bit weird just right now, but hopefully I time to show you what happens and why it makes sense. Okay, now let's go to the affine plane. So we have two coordinates, and we do the same computation. So the x bet, the the space, the part we want to remove is those where we have the center. So that's absolute value of T1 and absolute value of T2 smaller than 1. And so the part of infinity, the boundary, is this one with the max of the two coordinates is bigger than 1. Okay, and actually it's easier to draw things, to do it like this, to fix some real number r bigger than 1, and to demand that the max of the coordinates be equal to r. So you see that my x infinity is now the union of all x infinity r for r going to infinity. And maybe no, I want to draw a picture of this x infinity r, which is the more crucial thing to understand. So you see that you have this max of T1 and T2 is R. So you have two, I mean, so draw x infinity, no, yeah, x infinity R. So you have two parts. So you have the part where T1 is at most T2, and the part where T2 is at most T1. Okay, and you can also project on the two. Should I do it like this? Yeah. Yeah, sorry. Yeah. If you fix some r, yeah, maybe, yeah, let me do it in a different way. Sorry. Yep. If so you can project onto the either a T1 or T2, and you have yeah, maybe say so in A1 you have T1 equals R in A1. So that just gives rise to a point which is this R to the valuation of T1. But this time the R is fixed because I just fixed the R, and then the fiber over this point. Yeah, so the fiber over this point is just going to be some disk in the T2 variable. Okay, some disk of radius r. Okay. If you fix absolute value of T1 to be r by the projection to the coordinate over this point, T2 can take just any value from 0 to r. So just a disk. So you this way, and this is going to be a disk over the residue field of the point the point here. So this is now a point with a non-trivial residue field. So it's really some disk with a lot of branches. So this is one disk, and of course, if you project onto the other coordinate, that's like the first coordinate, you find a disk with the so if this point is I don't know, like this point is eta 1, so this point is a disk over the residue field of eta 1. So it looks like this. So that's some tree. So you have just two trees actually glued together that come to two disks coming from the two different projections. And actually, you recover here a picture that goes under the name of a valuative tree in the work by Favre and Johnson. Okay. Yeah. And now constructing the compactification. So far that was only the boundary, just some part of the boundary. And what I claim is that it's possible to get out of it, I mean, to add it in a natural way to the space you started with in order to get a compactification. How do you do that? So you start with the hybrid analytification of C, meaning that you start of X, so you start with X over the Banach ring C with this hybrid norm, and you look at the analytification. So it's the picture I had before, you remember, like all the complex spaces degenerating onto some non-Archimedean space. And then you start with this X hybrid, and you remove from that you can remove the part, the bet part in the fiber. So it would be something like this. So we had this picture of the spectrum that was like that. Absolute value here, usual absolute value, trivial absolute value. Like all your complex spaces, basically all looking the same, something, yeah, same form. And then some degenerate version of it here. And you only have this, you have this X bet somewhere here, maybe a bit bigger, and you only remove this X bet on the trivial part. So you keep all the complex part to be the same, and you remove the X bet only in the trivial part. And since this X bet was compact inside just one fiber that's closed, I mean, it's just compact in the whole space. So you remove some compact space and you still get an open subset. This X plus is an open subset, so it inherits an analytic structure and all the nice property of the Berkovich spaces, which is interesting. And so now you see that this does not look, of course, as like a compactification, especially because we get several copies, like infinitely many copies, uncountably many copies of the same space. Yeah, I mean, here it's all X of C with just different normalization. So we have a whole family of them. And of course, I mean, this is not what a compactification should look like. It's much too big. So what we do is okay, this will delete my picture, but never mind. So we just mod out by some equivalence relation between absolute value. Okay, and okay, so this will have the effect of, I mean, in my previous picture, just to identify all the complex the complex copies of the space, and it will also do something on the trivially valued fiber. Okay, so that's the construction. And yeah, maybe let me now tell you some properties of this construction. So the resulting space is a locally ringed space. So as I said, you have this structure inherited by the fact that it's an open set. I mean, and you couldn't push. You pass through the quotient, but you can push forward the structure sheaf. And we have a dense open immersion from the complex space you started with this complex topology and the nice function. When I say open immersion, I mean I mean that when you restrict when you have those global functions, the sheaf of function on X corner, when you restrict to this open part of X of C, you get the usual analytic function, of course, and this immersion is dense. The resulting space is actually compact. So you added something at infinity. And okay, something about the topological dimension. Yeah, Steam is starting to run a bit late, so I don't want to insist on everything. What kind of other nice properties you have? You have this kind of functoriality property. So if you think a bit about it, if you really want to compactify, to have compactification, I mean, it cannot be just functorial for everything. I mean, it would not make so much sense. I mean, and so, but it can be functorial with respect to proper varieties. So if you have to proper morphism, so if you have a proper morphism between two varieties, then passing to the compactification, you still get a proper morphism. And since everything is basically termed in terms of phrased in terms of valuation, not so difficult to prove. It somehow boils down to the evaluative criterion of properness. And this association, so from X to X corner, preserves many properties. Why is that? It's because we're starting with some analytification procedure. Okay, maybe it does not look so much as an analytification procedure. So you start from X, and then you have several copies of X of C, and you add something on non-Archimedean, but still it's an analytification in Berkovich setting. And as such, as an analytification, it preserves a lot of properties exactly as we are used to in the complex setting. So if you start with a normal variety, the analytification is normal, same for regular, same for smooth, from blah, blah, blah. And so this will all be preserved in my compactification. And you also preserve some sort of modular interpretation. So this is just a bit loosely phrased, but exactly by putting all this together, like if you have a family of curves over your base, so of projective curves, and if you compactify everything, the fact that you have this proper morphism, so you can compactify at the same time both the base and the total space, because the morphism is proper. So on your compactification, you end up with some fibers over your locus in the boundary. And if you start with curves, what you get on the boundary is just analytification of curves. So if you start with a moduli space of complex curve, you end up with a moduli space of curves, except on the boundary, you will get some Berkovich curves, so over non-Archimedean fields, but it will still be curves. So something you can understand. Yeah, so that's basically what we wanted to have. Okay, and maybe I'm going to show you what it looks like on some examples. So let me start with the affine line. So then, so you remember that we have this, no. So we had this x infinity that was just something like this, just some open segment. Yeah, I think it was blue before. Some open segment like that with r to the degree. But you see that I said I should mod out by equivalence of semi-norms. So actually those absolute values are equivalent. They just have some different normalization. So when you pass to the quotient, you just get exactly 1 point. Okay. And that's what we want, actually. I mean, of course, we know how to compactify C even as a variety. So we just want to find something close to P1 of C. And what we do here is we just add 1 point. So exactly as we are used to, as we want to do with the point at infinity. And this point here, the nice thing about it is that if we have a coordinate T here, this will have some residue field with C double parenthesis, T minus 1. Okay. So telling you something about the behavior of the function at infinity. Okay. And this also work in the relative case for meromorphic family of spaces, just somehow by functoriality, as I said before, of the proper maps. And this is related to some work by Buxon and Johnson. Maybe one more picture here. So something that's nice here is also if you you change coordinates, you say maybe u equals t to the -1, and you localize around the point at infinity, it looks like you've done the following things. So you start with some puncture disk. Okay, so this is a puncture disk, D01 with 0 removed. And then, and what you do, so you have some 0 removed here, and I add here in the middle my blue point with the residue field C double parenthesis, so I say U. So here you have coordinate U. Okay, so it's really the disk and with a point missing, and in the center of this disk you plug in a point with this residue field. And this is what works, and this is what the Buxon Johnson do. Actually, I mean, in slightly different language, but you can do that in a relative way. So if you have X, some meromorphic family over some puncture disk, so it's something, I don't know. So this is a puncture. So you have a lot of spaces everywhere. Okay, and then you add the blue point, and you end up with some Berkovich spaces in the middle. Okay, and which is a Berkovich space over over C double parenthesis U for this residue field. Okay, so this is what the compactification does for you in a quite natural way. Okay, so this was the case of dimension 1, but of course you can do it in higher dimension 2, so which doesn't appear in the work by Buxon Johnson, which is really only devoted to this case of like one-dimensional degenerations. And so we can have a look at what happened for the affine plane. Do we? Yeah, I'm not sure. So I'm running a bit out of time. I should maybe choose what I'm going to say or not. Yeah, but basically I already did everything we wanted. So you start with the affine plane, and then when you mod out, so we describe this x infinity like this boundary with the max of the absolute value of the coordinates being bigger than 1. And modding out by the equivalence of absolute value is just like picking one R, and you have exactly one representative of each class that has absolute max of the absolute value of the coordinate being R. So what you add at the infinity is really this space, and this is the evaluative tree by Favre and Jensen. So you have yeah, maybe I can do so. See if I want to draw a picture. So you have this. I'm not sure how to draw a two-dimensional space. You complex space. So this can be some I don't know, some x of dimension 2. And at the boundary, you have this space by Favre and Johnson, which is some valuative tree, which at least in my mind looks like this, like two disks glued. So something dimension 1 going glued at the boundary. And it's interesting to see that. So you have this natural boundary, and that knows about some properties of your spaces. And for instance, the points at infinity, I mean, so you can go. I mean, I said that the complex part was dense in the whole space, so you can go towards the point at infinity, but maybe in different directions. And what I want you to point out is that the points at infinity do somehow keep track of the asymptotic relative logarithmic growth. So you can go to infinity with different speeds with respect to the different coordinates, and those points keep track on how those speeds are related. I wrote down a small example on the bottom of the slide. So if you consider the sequence 2 to the n, 3 to the n's, so it goes towards some point in the boundary. I mean, it is compact, so you have to go somewhere. And the thing is that if you look at the ratio of the log of the absolute value, it's always log 2 over log 3. So you can compute that on your point at infinity, and you say, okay, if I get to this point by some sequence, probably I had some relation between the speed of convergence toward infinity, like the divergence speeds, that were somehow in this ratio everywhere in my sequence. Okay. And yeah, so that's about to tell you I mostly considered so far topological properties of the space, and there are also algebraic properties. So that, yeah, I'll just phrase this as some kind of algebraic bonus. Just why bonus? Because I mean, so far, I mean, I find this quite interesting, but I don't really know how to use this concretely at the moment. But still, yeah, let me do it. So you start with a current sheaf on X, so algebraic thing, and you can get from that a current sheaf on the compactification. Same procedure as before. I mean, you need to keep in mind that everything comes from some analytification. So if you want to, if you analytify, you can always analytify current sheaves. I mean, they're certainly familiar. And so you can analytify current sheaves, and then you can restrict them to this open part we had. and pass to the quotient. So it's quite clear, just the general procedure gives you a sheaf on the compactification and it's current. I mean, if it's built from copies of the structure sheaf in the start, it will be built from copies of the structure sheaf um, at the end. Okay, and so we have kind of partial Gaga results. I kind of expect that we have full Gaga results, except that I cannot prove that. But so the first thing is that the functor from a current sheaf to the compactification of the compactification is an equivalence of categories. So you really have the same sheaf on the also on X, so meaning on the algebraic part and on the compactification. And second thing, the global sections are the same. So like a full Gaga result will tell you that all the higher cohomology groups are the same, but I don't know how to prove that. It's a bit tricky, I guess. And so that's nice, but I mean, it tells you something maybe a bit counterintuitive, is that this compactification actually looks algebraically just like X itself. So in some sense, we did not really compactify. That's a bit weird. Like you could, for instance, expect that all the cohomology group to be finite dimensional, something like that. So this is false. Of course, if you start with X affine and you get the same thing, you get something infinite dimensional. But it somehow means that, I mean, if you get like some kind of a universal compactification, you should keep track on the properties of X itself and not on all the possible compactification. Okay. And yeah, so this is quite an interesting result. And just to tell you a bit more what it means, I think I did, yeah, in the case of the affine line, if you look at the functor from the coherent sheaf, so a coherent sheaf on the affine line, just some module of finite type over C adjoint T. Okay. And if you look on the compactification, what is a coherent sheaf? So you get a module of finite type over C, like C, but the usual C with the analytic topology. So some module over the entire analytic function. So analytic function that converge on the whole plane. So you have a module over that you need somehow to glue with this added point. So like some module, some vector space over C Lorentz series with the variable t minus 1 and compactibility conditioned. And the result tells you that, okay, the data of those things are actually the same. Okay. And I mean, here it's already not so difficult. Going to higher dimension is a bit of a mess, but that's I mean, a bit more complicated. And here you see what happens. Or if you want to compute the global sections, you see downstairs you have like some entire analytic function. And you want at the same time that it belongs to the field of Lorentz series with variable t minus 1. So meaning that when you go on the left, like the polar part of your Lorentz series, I mean, it's finite. So you only have finitely many terms in negative powers of t minus 1. So meaning that only finitely many positive terms. So it has to be a polynomial. So it's really a mix of two things. Analytic conditions on the complex part and something more algebraic on the boundary, something like telling you that you have basically you don't have essential singularity, only meromorphic singularities. That's something pretty similar that happens in every dimension. Okay, and yeah, that's the way it works. And what did I? Yeah, I think I had some application to logarithmic degeneracy after that. But it's, yeah, I think it's almost time to stop. Yeah, let me maybe. No, I think it's probably probably enough just to tell you about this compactification and the way about the general property. So that's really some kind of overview about what you can get from so just a general compactification theory that should have hopefully quite nice property. And I hope that it can be also useful and used in several different contexts to try to compactify all sorts of objects and especially moduli spaces and get some more grasp on them. Yeah, I think I'm just gonna end up here. And so thank you for your attention.
Yeah, thank you very much for the very nice talk. So is there any questions from the audience? Oh, there's a question.
Do we have homological machinery to work? What about homology or cohomology machine?
Yeah, so I'm not sure exactly what you mean, but I mean yeah, you certainly do. I mean, so you have all current. I mean, it's yeah, it's a locally ringed space with all nice properties. So you can write down a resolution of sheaves and injective sheaves and whatever. So you can define all the like cohomology on every sheaf you like here. And for instance, I'm not sure if it's going to answer your question, but something I wanted to do like. If let me try to write down something maybe here. If so you see that you have this compactification, so you get from you have X this compactification is just the complex part union the like the boundary. No, let me put it like this. Okay, and you can I mean, one of my hope is that it's possible to compare the yeah. So if we have some kind of full Gaga theorem, like the cohomology of the compactification is just the cohomology of X. So it's basically here is as if I've written X as a union of the complex part with the complex topology, the complex cohomology, and some other part, a bit weird, but never mind. And so it would be also a tool like to compare the cohomology, the algebraic cohomology and the analytic cohomology. And probably if I try to do it like this, I'm just gonna mess up thing. But you can write down some exact sequence when you so I don't know, like you have the H. So you go to restriction. So you have the HI of I don't know the. Yeah, let me not put coefficients, but like this compactification going to the HI of the complex part. Okay, with some coefficient, right? And then going to probably you want like some HI plus 1 with compact support in the boundary, something like that, right? And the nice thing would be that if this here is equal to the cohomology of X itself. So you see it tell you something between the relationship of the cohomology of X, the cohomology of its analytification, and you can somehow control the defect. And okay, so but you can certainly compute a lot of cohomology I mean cohomology certainly exists. You can define the cohomology groups, no problem, and hopefully you can even do something with them like this way.
Once again, the left-hand side vertical is always true. I mean, compactification and non-compactification, the cohomology is always the same.
No, that's what I put a question mark. I believe this should be true, but I did not manage to prove it. So I can do it for H0, which is not much, but it's already something. But yeah, I think this should hold. But yeah, not I don't claim I can prove this at the moment.
Okay, any other questions from the audience?
Can you explain a little bit about how the regularity of the compactification is preserved?
Uh,
From the affine line compactification, it is quite clear because
Sure.
it's like the boundary is identified to a point, and then you have something like a P1. But then like the copy of C with that trivial norm, it doesn't look very smooth to me. So I don't know, like, if we're considering a different example, then yeah, how would the compactification be smooth for a smooth variety in general? Yeah.
Yeah, okay, so it depends what you have in mind, but yeah, I agree that from the topological point of view, that it yeah, when if you look, I don't know, at those pictures, I had so some time ago, but like even the first one, where was it? Not this one. Yeah, exactly this one. Probably this does not look so much like a smooth picture, right? So you have all copies of C, and then somehow it degenerates. But well, so you have this degeneration. Sorry, this general definition of Berkovich spaces over. So the Banach rings, and in this setting you can define a notion of smooth space and a definition of étal space, of étal morphism. Sorry, actually it was done by one of my PhD students, Dorian Berger, who tragically died like 3 weeks ago. But it's so there is this notion, and which is so I mean the étal morphism is basically the usual stuff. You need to phrase it algebraically. Yeah, you have it's. I'm not sure how familiar you are with all those Berkovich spaces and everything, but there are locally ring spaces. So you have a notion of flat morphism. Just look at the morphism induced between the local ring. You have a notion of ramification, and so you can just define étal as being flat and then ramified. And then it turns out that if you analytify an étal morphism, at least in this setting, by Dorian's result, it's still an étal morphism. And for regularity, yeah, it's exactly the same. I mean, I just look at the local ring. You can define the local rings everywhere, and you can prove that the regularity of the local ring is preserved because it's preserved by analytification. Okay, so I mean that I'm not sure how much I do answer your question. So I mean the proof is written. I mean that's no doubt about this, but it's tell you something about like the local ring if you want. But I'm not sure what the topological meaning of the notion would be if this is the question. I mean, I've spent I don't know like 20 years of my life working with Berkovich over Z, Berkovich spaces over Z over C hybrid, and I have an extremely hard time to understand what's going on from the topological point of view. I mean, I understand well enough to be able to prove a few things, but the way it really behaves in family is really, really tricky. But okay, but so now if you forget about the topology and look only at the algebra, maybe it's a bit clearer that the local ring should be quite nice. So it just said that here, like if you look at a point on the non-Archimedean fiber, the local ring is somehow a mixture between something like being on the non-Archimedean side, you just basically have power series with just no convergence condition. But the fact that you, if you take a local ring, I don't know if you take a point here, you see so neighborhood, it's going to be like this. So it meets a bit. You end up having some part of C inside. So the local ring is going to be some power series with some condition coming from the fact that you have some complex part in every neighborhood. So like some just positive radius of convergence, something like that. It could be a bit more tricky in higher dimension, but that's something like that. So that's just telling you some regularity of some rings of power series with some additional conversion condition, I would say. So from the algebraic, it's pretty easy to believe it's going to be regular. From the topological side, I'm afraid I have no idea.
I see. Thank you very much.
Any more questions? Maybe I have so question about this curve case, which you said, yeah, and for the curves we have canonical compactification and also kind of looks similar in flavor. So is it compatible somehow?
Well, yes and no. I mean, it's topologically. I mean, so I can if you start with some say, yeah, smooth curve, yeah, to make them simple, but you just get something very similar to the compactification you would expect. I mean, so in the algebraic case, you just have, I don't know, if you add n points, then this compactification will add basically also n points, except they are not going to be C points, but non-Archimedean points, so points with residue field being the thing you expect. Like if you remove some point, you start with a curve, you remove some point A, you're gonna end up with a residue field that's like Lorentz series in T minus A, something like that. So just in this case, it's very similar, but it's also not completely the same thing. And I mean, it's also interesting that it's not the same thing, because if I get back to that was also the I mean, so you have more. I don't know if you have more or less or information. It probably depends on the way you want to look at it. So it's, I mean, in what I do, you lose some of the nice property of the proper varieties. Basically, the fact, mostly I would say, the fact that you don't have finite dimensional cohomology, but you get some information about how you about the degeneracy, like in the, where was this? Probably, yeah, no, probably here in no, this Buxton Johnson stuff. I had some picture, yeah, like that. You see, if you do this picture, like if you look at a meromorphic family of spaces, just with some meromorphic singularity, I mean, there's no way you can do or yeah, maybe you can, but like not unique way to compactify the family over like the disk with the point added. And or if you do that, I mean, okay, you just have one fiber, but what are you gonna say about it? And whereas if you do this with this procedure, the fact that you have a bigger residue field, so with some additional non-Archimedean variable, tells you that the limiting fiber records a lot of the asymptotic behavior. Okay. So I mean, if you just dimension wise, it really the same, but like you can do also dimension one, and but some relative thing of a dimension one, and this is where it becomes more, things become more interesting, I would say.
I see. Yeah, thank you. Any more questions from the audience or online? No? Yeah, then one more question.
I'm curious, is it understood what happens with the moduli space of curves if you apply this compactification, and how it compares to the Deligne-Mumford compactification?
Well, that's of course, yeah, quite a nice question. So if you do that, yeah, I mean, as I said, I'm not sure how to describe exactly the boundary, but okay, this is not so much of a problem, but yeah, okay, maybe let me yeah, one like technical point is that so it's a stack and not exactly a variety, but let's pretend that it is, and that we have a universal family over that. I'm pretty sure you can get rid of the technical complication just working with local charge and doing a few stuff. That's probably not where the real difficulty lies. So if you do that, so you're gonna end up with some compactify moduli space. With the compactification. And as I said before, if you have a universal curve over that, you're going to end up with universal curves over the compactification. So you have your boundary, which is some Berkovich space of dimension, I don't know, yeah, same 3G minus 3, maybe minus 2 topologically. And over each point, you have a Berkovich curve that you can, like a smooth projective Berkovich curve that you can look at. So it's a bit weird. I mean, so it's not, of course, Dölin-Mumford compactification. You really have a smooth non-Archimedean curve and not a stable curve, right? And so that's not the same thing. And on the other hand, oh yeah, maybe I could have said this too. You certainly have a map to the Dölin-Mumford compactification, except that I don't understand it so well. The thing is that in general, so yeah, I could have said that maybe there is a relation between the Berkovich spaces and like the Zariski-Riemann space. Berkovich spaces is basically a space of valuations. And so if you look at a point in your compactification, it's some sort of valuation, and maybe it's a valuation on the field of function on the space, so of your moduli space of curves, and then as a valuation, it has a center on any compactification. So you start with a point, and you can look at its center in the Dölin-Mumford compactification. So you have a map. I'm not sure I can say anything really interesting about this map, but so I expect to be relationship like if you have this non-Archimedean point, a non-Archimedean curve over it. So if you're familiar with the Berkovich curve, maybe you know they have some kind of skeleta, which are like finite graphs, so a tropical curve, something like that. And this finite graph should be, just as in Thuillet's results, the dual graph of, I guess, the stable curve in the Dölin-Mumford compactification. But it's much bigger. That basically in the Dölin-Mumford compactification, so you will find some stable curve. So you can go to the dual graph, and there are many Berkovich curves that have this same skeleton. So it's really something much bigger. But if I may say one last word on this, I don't know if you're familiar with the work by Amini and Nicolosi. They also want to compactify the moduli space of Riemann surfaces, say. What they want to do is to compactify it in a way that you have some continuity of some measures, like the Bergman measure on the Riemann surfaces. You want them to be able to extend them by continuity, and it's known that you cannot do it on the Dölin-Mumford compactification, because if you approach the boundary, like the same point in the boundary of the Dölin-Mumford with different speeds on different variables, the limit should be different. So you need a bigger space. And so they somehow do it by hand, and with it's like my last slide, something like that. If you with this space, this is some joint work with Robert Wilms. We do the same. We can prove that the canonical measure on the Riemann surfaces do extend to canonical measures on the Berkovich curves. So there is this works too.
Okay, thank you. Yeah, I've worked with Omid before on a project, but I haven't. I should look more into his work with Nicolosi to.
Oh, okay, yeah.
And
I mean, if you
understand
want to
this,
be
so-
more, so
Right.
yeah, I mean, Nicolosi have a quite intricate compactification in several steps, and I think this theory here just gives you like basically the first step of the compactification, but where it's already enough to have to extend the family of measures by continuity.
Okay, all right. Thank you. I appreciate it.
Any more questions? Yeah, maybe one last thing. I just realized I don't fully understand. So you mentioned properness, you have functoriality, but what happens with open immersions? Like, if you have a dense variety of like an open subset in a, it's weird. I don't know.
No, yeah, I said it a bit quickly, but so I don't, I mean, I don't think it's, I'm not sure what to expect. Like if you,
Because I mean, then
it's not-
birationally equivalent varieties would all have the same compactification or something like this, which sounds weird, right?
Yeah, so that's not the, yeah, and the thing is, if you yeah, you see what happened if you take okay, like the some open even some open disk, I mean, or you take some variety and you just remove a few points in it. And then if you take the compactification of the smaller variety, what you get is you will have added some non-Archimedean points to this one. And so these non-Archimedean points, you cannot really map them to the complex points you had before. So
I see.
like it's
Weird.
somehow if you want or maybe in some different category, but I didn't work that out. I mean, it's not clear. Like it's if you take something smaller, somehow going to the bigger variety you had before is already a choice of a compactification, and the one I have like does not choose a compactification. So you want to restrict generality at some point. I mean, so you have a weird map, forgetting some on the info and going and keeping the other.
I see.
I think you could do probably like a partial compactification, the saying I want to compactify along this direction or along this divisor and not this one. But
so maybe it's still true that birational varieties have bimeromorphic compactifications, or not even clear.
Sorry, say it again. So birational.
Birational varieties have bimeromorphic compactification.
Okay, yeah. Yeah, maybe I should refrain from answering this in like such too strong. But yeah, I think it should be. I think it should be fine. But yeah, I should really.
Okay.
Yeah. After like 1 hour talk, it's always difficult to
Okay. Yeah. Sorry.
be sure about things.
Also,
So yeah.
Yeah. Okay. Also, too many questions already, I think so.
No, that's fine. But no, that's a nice question. But I should think about it before I say something definitive, I guess.
Okay. I think. Thanks. Okay. So, any more questions? I think not. So yeah, thank you very much for the nice talk and for answering all the questions. Thanks. Let's thank the speaker again.